Hi, hello everyone. The topic assigned for us is Booth algorithm. I'm Gopikashri. Let me give a quick introduction about what is Booth algorithm. Booth algorithm is a method for multiplying binary number, whether it is positive or negative. It streamlines the multiplication process by decreasing the number of addition. The algorithm will works well with the signed number as well as the unsigned numbers using 2's complement representation, making it efficient for handling the sequence of consecutive ones in the multipliers. This approach is particularly useful in enhancing the speed of binary multiplication in computer processes. So, over to Shalini.
Binary multiplication requires shifting and adding multiplicand for each one of the multiplier, which means like we have both rules of binary multiplication and binary addition. So if it's like 0 into 0, the result will be 0 in multiplication. 0 into 1 will also be 0. So basically it will follow the AND gate. Only when it is 1 cross 1, the answer will be 1, which is true. Traditional methods are time consuming with multiple additions and shifts. Booth algorithm optimizes the process by recognizing patterns in the multiplier. It reduces the unnecessary shift and operations for consecutive ones. So how it reduces the unnecessary shift when there is consecutive ones is that it will just ask the multiplicand to shift by 1 such that consecutive ones operations can be neglected. Particularly useful for signed binary numbers and large multiplications. Next slide. Key concepts. So this is the flowchart for Booth's algorithm. So Booth's encoding operators on bits like bit pair from multiplier. So based on the pair from 1 up to 3 operation, so addition, subtraction or no operation. So when the multiplicand is like 0, 0, 1, then the multiplicand will be added. And then when it is 1, 0, the multiplicand will be subtracted. No operations will be performed when it is like 1, 1 or 0, 0. That is consecutive 0 or consecutive 1. So this approach helps in skipping over blocks of consecutive ones and optimizing the performance. Next slide.
So, I'm starting for Booth algorithm signed multiplication. So I'll give a short introduction about what is Booth algorithm when it is come to signed multiplication. Booth algorithm is a type of method that applies a similar approach to multiplication. It has an advantage of accelerating multiplication process, making it highly efficient. This algorithm specifically used in binary multiplication involving the signed numbers. Booth algorithm can be performed for negative and positive numbers too. So next comes the step. I'll just tell you the very important conditions on step. So initially the value of a will be 0 and the value of q minus 1 is also 0. The multiplicand and the multiplier. For example, you just imagine you are performing a problem on Booth algorithm. Your question is 5 into 3. 5 will be the multiplicand. The binary value of 5 will be the multiplicand and a binary value of 3 will be the multiplier. The multiplier's last digit that will be either in zeros or ones, and the q minus value will be checked for this condition. If it is 0 and 1, the condition will be a plus m. If it is 1, 0, the condition will be a minus m. If it is 1, 1 and 0, 0, you can just simply use this right shift operation. And that's it about the flowchart. As Shalini explained before, these both have the similar conditions over here. So, example of Booth algorithm where I have taken a number, an example called minus 5 into 4, which is obviously 20. I have used both, I have performed Booth algorithm for the negative number. First we need to convert the number into binary number. So the binary value of 5 is 1 0 1 0 1, and the binary value of 4 is 0 1 0 0. 4 can be represented as Q here to perform the main operation in the Booth algorithm. So the binary value of 5 is converted to converted to 2's complement, which is identified as M. So this part is only used in one part of the Booth algorithm problem. So we'll just discuss this later. So let me, as I told in the flowchart, we have 4 conditions. So the same I have written it like I have shown it here also. The initial value should be taken as value of A should be taken as 0, and the value of Q minus 1 is also 0 initially. As the problem goes on, these both value will change accordingly. So let us go to the very main part of the Booth algorithm. So as I said, the A value is 0 initially, and the Q value is the binary value of 4. So we have given it here, and the initial value of Q minus 1 is 0. We should check for the last 2 numbers. It is 0 0. So the condition for 0 0 is shift right, and the operation shift right is performed here. This part will move here, and this part will move to the last position, and the Q minus 1 value will be shifted to the very first position of A. Then comes the next step. Again we have to check the last 2 values, and again it's 0 0. So right shift operation is performed. So as I told, this part is only used in a single part of the Booth algorithm. So as I said, the condition for 1 0 is A is equal to A minus M. To make it much simpler, we are taking it as A plus 2's complement of M. M is the value where we have I have told you before, that's 2's complement of 5. So again the M value will be converted into 2's complement. The 2's complement is done by converting the binary value into 1's complement. Then by adding 1, you'll get, finally you'll arrive to 2's complement. So the value of A, look for the value of A, it's 0 0, and the value of M, as I told, it's here. No, the 2's complement of M should be substituted here. So 0 1 0 1 is and you will have the value of A here, and you just substitute the value of A here, and shift right operation should be performed. After the operation of shift right, you can take this part to the next step, and again have to check for the condition. It's again it's 0 and 1. The condition for 0 and 1 is A is equal to A plus M. So A value is 0 0 1 0, and the M value is here 1 0 1 1. After adding these both binary numbers, you will get a new M value, and you have to substitute them here, and right shift operation should be performed again. The Q minus 1 value should be in the first position of the A. After all these steps, we have to take this 8 digits, and we have to convert them to 2's complement, so that our final answer will be here. Uses and benefits of Booth algorithm. Booth algorithm is a method that makes multiplying binary number easier, especially for the numbers with positive and negative sign. It works very well with the signed numbers because it uses the system called 2's complement, where it lets us to handle both the number involved with the negative signs too. This method also speeds up the multiplication process by reducing many addition to do with the large numbers because it's efficient too. Booth algorithm is often used in computer hardware like CPUs to make the multiplication process more fast. It can be also adjusted to work with large binary number, making it very feasible. Over to Shalini. Over to Shalini.
Booth's algorithm using Booth recording multiplier table. So this is another alternate method for calculating the multiplication using Booth's algorithm. So here we will be using the Booth's recording multiplier table. So which will be consisting of bit I minus 1 and the version of multiplicand selected by the bit. So as we know, Booth algorithm is an efficient method for multiplying binary numbers. Here, the recorded multiplier table is a key part of this algorithm as it helps in determining the operation based on the specific patterns in the multiplier's binary digit. The Booth recording multiplier table works like, for example, we are taking a normal decimal number 30 with base 10. So the binary digit for this decimal is 0 1 1 1 1 0 0. We will be performing the recording value. How we will be performing is that we will be appending an additional 0 at the least significant bit. Next to the least significant bit, we will be appending a 0 and then we will be calculating the recorded multiplier value. So, the last 0 to the next one. Okay, so 0 0 will become 0 and then 0 1 will become minus 1. So, by referring the table, 0 0 is 0, 0 1 is plus 1, 1 0 is minus 1 and 1 1 is 0. Okay. So yeah, so the recorded multiplier for 30 base 10 will be 1 0 0 0 minus 1 0. Similarly for 100, we'll be taking the binary number for 100 and then appending 1 0 next to the least significant bit, and then we will be multiplying, like checking each digit from the least significant to the most significant bit, we're checking and comparing each number and then getting the recorded value. Next slide. Example for Booth algorithm using Booth's recorded multiplier table. Plus 3 into minus 6. Okay, so plus 13 into minus 6. Plus 13, the binary digit according to the 8421 is that 01101. So the place value will be 1 will be there in 8 position, 4 position and 1 position, which makes 13. And we have taken it in 5 bit to know whether the number is positive or negative. How is that? Like for minus 6, we will be taking the 5-digit binary value for 6 and then taking the 2's complement of 6, which will make 6 to minus 6. So any positive numbers, 2's complement will be the negative number, as we know. So taking m as minus 6 and q as plus 13, we will be taking the Booth's recorded multiplier value for minus 6 and then multiplying it with the original q value, which is plus 13's 5-digit binary number. So 01101 into 0 minus 1 1 minus 1 0. We will be multiplying it from the least significant bit from the leftmost to the q's value or the q terms. So first we will be multiplying 0 with the q terms, which will make all the 5 digits 0. So here we are having a 5-digit binary number. To make it like in general, when there is like a binary multiplication, when we are multiplying two binary 5-digit numbers, then the resultant should be of 10 digits. So to get the value, we are extending the digit, like the value, with respect to the most significant bit. So for example, first we are multiplying 0 with q, and all the result is 0. So see the red markings, they are the extensions of the actual result, making it 10 bits in total, right? Next, minus 1 into q. Minus 1 into q is nothing but we will be writing the resultant as 2's complement of q. So 1, 1, 0, 0, 1. So here the most significant value is 1. So we are extending the remaining bits, which is 9 bits. The remaining 4 bits, already the 5 bits are the resultant, 4 bits will be the extension value. So the most significant bit is 1, so we'll be extending the rest with 1. Next is, we are multiplying 1 with q. So the same value will be resultant and the extension bit will be 0, as the most significant bit of q resultant is 0. Then again we are having minus 1, which is again the q 2's complement of q. Then here the extension of sign bit will be 1. Okay. And then at last we are again having 0 into q. So every all the resultant values will be q 0, and the extension bit will also be 0, and the most significant bit of that resultant is 0. And then we will be adding all the 5 extensions, like all the 5 resultants, using the normal binary addition method, which is like 0, 0, 0, and then 0, 1 is 1, and then 1, 0 is 1 again, and then 1, 1 will be 0 with carry 1. So by performing this binary addition, we will be getting the resultant as minus 75 in decimal, but actual result will be 1, 1, 1, 0, 1, 1, 0, 0, 1, 0. In simple terms, 1, 1, 0, 1, 1, 0, 0, 1, 0. So here the most significant bit is 1, which means that the whole binary digit is a negative number. Okay, if the most significant bit was 0, then it means that the whole binary digit is positive. So the most significant bit here is minus, so the answer we will be getting is minus 78. If the most significant bit was 0, then the answer we will be getting will be 78. So the desired output for plus 13 into minus 6 is minus 78, and we have got the desired result.
Of Booth algorithm. Booth algorithm is a technique used to speed up the binary multiplication process, making it very useful in high-speed computing areas. The high-speed computing areas in the sense digital signal processing (DSP), process arithmetic unit, graphic processing, and the graphic processing. The algorithm helps to speed up the task in graphics, such as image rendering, where fast multiplication needed in the image rendering processing. Booth algorithm is especially very helpful in high performance computing, where the speed is essential for them to complete their task. For example, it helps the modern processor handle complex tasks like video and audio processing very quickly. Over to Shalini.
Advantages and limitations. So advantages of both algorithm techniques are its efficiency. Reduces the number of operations, especially for the number of consecutive ones. So there will be no operations when the q naught and the q minus 1 value is either 0, 0 or 1, 1. So that is what they are trying to say here. It's efficiency. So work with signed numbers handles both positive and negative numbers. So in normal binary multiplication, it doesn't allow us to multiply negative values. Only positive values are allowed. So here it can handle both positive and negative numbers with signed operations. Next, optimizes binary multiplication. Fewer shifts and additions required. So, optimizes binary shift. So So here, as we saw, according to the flow chart, Q naught and Q minus 1. If it's 1, 0 or 0, 1, there will be either addition or subtraction happening. So with less number of shifts. So when there is no consecutive numbers in a binary digit, then there will be less number of shifts and there will be more number of operations where you will be getting the output in faster duration. Widely used integral in hardware for processes and digital systems. So Booth algorithm is used in the modern technology. Let it be the CPU, let it be any hardware components related to a computer. Then helps reduce time complexity for large binary numbers. So with the signed multiplication of Booth's algorithm, there will be like necessary shifting and necessary additions and subtractions, where the time complexity, which means the duration of getting the desired output, will be much lesser. Now coming on to the limitations, it's complexity. So more complex to implement and understand than the simpler binary multiplication. So more complex to implement and understand than the binary multiplication is that here we are dealing with positive and negative values. So there will be a need of performing one's complement and two's complement to change them to negative and positive and vice versa. So which gives you additional steps to get the desired output. Then sign extension issue requires careful handling of sign bit, especially for large numbers. So as I told, the example that I took, plus 13 into minus 6, we got the answer with the most significant bit as 1. So we need to mention the most significant bit as 1 and 0 for it to be negative and positive respectively. So the sign bit plays a major role. If you're going to shift it, then you will be getting a wrong answer, and the whole process will be a waste of time. Then, not always optimal. So for some multipliers, isolated ones may not gain much advantage. So similar to what's been said before. So not always optimal for some multipliers. So when there is isolated ones, like not even number of bits or some kind of an issue, might lead to a incorrect resultant. Then requires accurate management of extra bit. Yeah, so we can make the bit to any odd number of numbers. Like for example, generally a number for any number, for example, generally if it's like in the method of 8421, right? So if we are taking it in an odd number of bit, then the accurate management should be there. We are taking the fifth bit as the most significant bit to just tell whether the number is positive or negative. You are not going to store any value which is going to affect the actual value in decimal terms. So accurate management of extra bit is very much important. The efficiency gain may not always justify the added complexity. Efficiency gain may not always justify the added complexity. It's like when there is n number of shifts and there is less number of additions or subtractions, that time there might be any incorrections in the methods we are solving. So that at last we have come to the conclusion. So Booth's algorithm is an effective method for multiplying signed binary numbers, as we saw in the introduction part. And in many other places, we have seen that it can, support both positive and negative numbers, right? And reduces the number of required operations in optimizing the binary multiplication. So it like on comparing with the signed multiplication method with the binary decoded method, the number of steps, the shifting, the subtraction, the addition is much more in the signed multiplication method rather than a recoding method. Then efficient for both positive and negative numbers using 2's complement. So when there is a positive number or a negative number, it can be shifted into negative or positive using the 2's complement. So if we are gonna take a 2's complement for a positive number, it is gonna result the negative of the same number, and if the same with a negative number. If you are going to apply 2's complement to a negative number's binary digit, it's going to result a positive number of the same normal positive digit. It's widely used in hardware like CPUs and DSPs, providing its real world importance. So as we saw in modern applications, it is being used in the various modern applications, and futuristic scopes are much more for this Booth algorithm. And though complex, its significant performance benefits in specific cases. So here we are dealing with positive and negative number. This is a repetitive statement for Booth's algorithm. It's complex, but there are n number of filtrations which can lead to a filtered and a clear-cut answer or a resultant where the verifications are possible, and even though there are n number of steps, we will be getting the desired output in a desired way and efficient way. Thank you, guys.